Okay, hello everyone. Welcome to our fifth lecture in ECE 576, Information Engineering. Before we start today's lecture, some people had questions regarding the previous quiz. So I'll try to get to those in a moment before we can start our discussion on the new topics. So the first few questions in the quiz basically were really following our lecture. So it involved computation of joint entropy, conditional entropy, and then the mutual information. So the real issue comes up with finding the conditional entropy. And as I told you in the lecture, you have to be a little careful because that requires computing the conditional probability density function first before you can do the conditional entropy. So I'll just quickly, based on some students' requests, I'll quickly go over how to approach those problems. So there was a question in quiz 3. Well, it's basically 1, 2, 3, and so on until I would say 4. So 1, 2, 3, 4. So there were 2 random variables. One is y and x, and each of them had 4 values. So 1, 2, 3, 4, 1, 2, 3, 4. And the probabilities were 1/8, 1/16, 0, 0, 0, 1, 4, 1/16, 1/16, 1/32, 1/32, and then there was another 1/16 here. The others were 1/32. So the first question says, find the joint entropy of x and y, right? So I'll say Q1. So there's several ways you could have done it, but I think since you have all the probabilities, you could simply use the formula for the joint entropy and find out what the h of x and y is, and that would have been just double summation. So it would have been just sum of x and y, p of xy, log base 2 of 1/p of xy, right? So that could have done the trick. Now the next part is about, so Q2 is about finding the conditional entropy of x given y, right? So that's a little more tricky because that involved basically, so it's essentially finding the expected value of 1 over probability of x given y. Okay, so basically we would find what is the probability of x given y is a certain value, right? And looking at the table here, y could take values 1, 2, 3, and 4. So what I immediately know is that I will have multiple values for y equals to 1, y equals to 2, y equals to 3, and y equals to 4. Right? So this, I'm talking about this small y. this guy here. So this guy can take 4 values. So for each value, we will have a certain probability of x given y is this value. So let's say y equals to 1. Then our conditional probability is basically probability of x and y divided by probability of y equals to right. The same thing for the others. So basically, you will have a density function for each value of y. Okay, so remember, these are density functions because this joint density is actually, so if you pick y equal to 1, basically, this is the probability of x comma y equal to 1. And so let's say this is probability, right? So that's like a density function. It has 4 values. And the value of probability of y equals to 1 is actually just the marginalization or the sum over all the x's. Okay, so if you sum them all, you will have probability y equals to 1, right? So if you look at it, basically, it's going to be 1/4, right? If you just sum it up, so let's say what is probability y equals to y? This is 1/4 here. If you construct a 4th column. Okay, so if I go ahead and write this, basically the probability of x given y equals to 1 will have 4 values, right? So x is 1, x is 2, x is 3, x is 4. Okay, so what it will be is 1/8 divided by 1/4. So that's going to be 1/2 here. For the second guy here, we're looking at this value divided by 1/4. So that's going to be 1/8. And then the third one is going to be 1/16. No, it's sorry, this is 1/4, and these are 1/8, if I am correct. Yeah, I think these add up to 1. Okay, so this is basically your conditional density given y equals to 1. So what you can do is basically find what is the entropy. The conditional entropy given y equals to 1. Right, that's simple because you've done it. You can do half log of 2 plus 1/4 log 2 of 4 plus 1/8 log 2 of 8 plus 1/8 log 2 of 8. So that's going to be some number. So same thing, same idea. You have to find probability x given y equals to 2. That's going to be another some numbers here. That's going to give you h x given y equals to 2. Right? And then the same idea. And all of these can be figured out from here. You have this, you divide it by the probability of y, you will get the conditional density of x given y. That's how you come up with these conditional entropies. So x given y equals to 4. Oops. Okay, and finally, your joint entropy, sorry, the conditional entropy H x given y is actually the sum of y, sum over y of these conditional entropies along with the probability of y taking those values. Right, so that's going to average it out and you will get the conditional entropy of x given y. Now the question 3 asked you about the mutual information. Right, so that's pretty simple because as I mentioned last time, it's just h of x minus h of x given y, right? So this coming from the first, I mean, you will have to compute it. And then this is from Q2. Okay, and this one is basically the sum of log 1 over the sum over all x. Okay, so hopefully if you do this, you can easily figure out the mutual information. The most tricky part is this second one, where you had to first compute the conditional density function and then move on to the entropy, conditional entropy. So I hope whoever asked this question is now clear about it. And if you have more, feel free to jump in. Okay, so that's our discussion about the quiz, and I just want to caution you because I feel some people are collaborating on the quizzes and you know, sharing of information is there. So just beware. I may end up selecting few people randomly and ask them to solve those questions for me. So I hope no one is collaborating and using unfair means. Just be responsible and I think a graduate class is not meant for good grades. You obviously need good grades, but there are more important things that you have to learn. So try not to use any of those means, otherwise you will be in trouble. Okay, so let's start our discussion about channel capacity. What we have seen up till now is the formalism. We have seen how to quantify information using the entropy measure. We've looked at variants of entropy like the conditional entropy. We've seen joint entropy, and we also saw what is mutual information. So essentially we are talking about communication over, right, over noisy channels. And remember, these channels can be anything. It could be the wireless medium. It could be the hard disk that you store data on. That's another channel. And whenever you're transferring data from a hard disk or a USB or a CD, basically you're communicating information, right? And there's a channel in the middle. So it's important to understand how can you communicate that information reliably over that channel, which may have some noisy elements. So the big picture is the following. Remember, we have an input data stream that we pass through a noisy channel, and then after some processing at both ends of the channel, we get an output data stream. Now, we are putting information on a channel at a certain rate, right? So this input data stream is coming at a rate of, let's say, like 1,000 bits per second, right? Or whatever rate there is, you kind of input the information on the channel at a certain rate. And what you're interested in is the output data rate, right? So you want to find out what the R is at the output. And this R basically is the rate of reliable data transfer. Okay, so the important thing here is the reliable part. Obviously, you can have as much data rate as you want at the output, but that may be erroneous. So you're interested in reliable data rate at the output. And important part here is that the maximum rate that you can achieve is actually called the channel capacity. So maximum rate of reliable data transfer is the capacity. So if you recall our our figure earlier between the rate and the probability of error, the capacity C is the maximum rate for which you achieve zero probability of error, or almost nearly zero probability of error. So that's intercepted the x-axis of your rate versus probability of error curve. Now let's look at an example to see how can we compute these sort of channel capacities, and how do we figure out what rate you can transmit over a particular channel. So we will take an example of the our favorite binary symmetric channel. Okay, so consider a binary symmetric channel with bit error probability f equals 2.1 and input symbol probability or probabilities of x equal to 0 being equally likely as x equals to 1, which is 0.5. Okay, so if you're sending an equally probable symbols over a binary symmetric channel, so what that means is you have a channel that looks like this. So there is a 0.1 chance of an error, 90% if you transmit 0, it's going to be 0, and 90%, if you transmit 1, it is going to be 1. But the input probabilities are equally likely. So it's 0.5, and probability that x equals to 1 is also 0.5. Now, this diagram here just illustrates what the conditional probabilities are. So it's a nice way of expressing what the probability of y given x is, right? It just summarizes what is the conditional probability of y given x. And at the output, so if you want to compute and probability y equals to 1, can someone help me compute these? So I'm looking for some help here. How do I compute probability y equal to 0? I mean, I have this information with me.
We can kind of invert Bayes' rule to solve for that probability.
Yeah, perfect. So how would I do it in this case?
I think in this case it would be probability of, let's see, y equals 0. Y equals 0 given, let's see, x.
So I mean, we're looking at probability y equal to 0.
Right.
Something like this.
Yeah.
So given x, right? So x can be
equals 0 in this case, and then the probability would be x equals 0 after that. Yeah, exactly.
Yeah. So so that's kind of averaging of the conditional probabilities. Okay, and we know all of this through this diagram. So y equal to 0 given x equal to 0 is 0.9. Right? There's no error here, and then let's multiply by 0.5 plus 0.1 times 0.5. Right? So that's going to be turns out to be 0.5. Okay, so similarly, probability of y equals to 1 is what?
Pretty much the same thing, except that we're swapping in y equals 1 into that expression you just wrote.
Yeah, but the thing is, once you have found out probability y equal to 0, you can just
Right. Yeah, subtract by 1. Yeah.
Which is just the same thing, right? Okay, so interestingly, you input equiprobable symbols, and when they go through a binary symmetric channel, they're still equiprobable. Right? So there's no change in them in terms of the likelihood or probabilities. Now let's try to compute what is the joint entropy between x and y. So what would be let's use another pen here. So if you want to find what is the h of x and y, how would you do it?
We find h of x minus the conditional probability of h of x given y.
Can you say it again?
We need to find the probability of the joint probability, the probability of h of x minus just h of x
Okay, h of x. Okay.
minus h of conditional h of x given y.
Yeah, I mean, you could do it. Right. So basically, so that's going to be the information, not the joint entropy. Right. So remember, there's a a circle here with h of x, h of y, and in this part here, that's h of x given y. And this part here is the information of x, mutual information between x and y. Right?
Yes, yeah, you're correct. Yes.
So maybe I didn't mention this earlier, but I should, or maybe I did, I forgot, but basically the joint entropy is whatever is inside, right? So all of this is the h of
Or we can find h of y given x plus h of x. And we
so what happens is it can be written as h of x plus h of y
or h of, yeah, given x.
minus the mutual information, right?
Can it be h of y given x, a conditional
So-
probability, which is, yeah, says the same as h of y minus information.
So basically this one is what? This can be h of y minus h of y given x. That's the
Given x.
definition.
Yes,
Right. So what we will end up with is h of x plus h of y given x. Right.
yes,
So again, looking at the this chart here, that's the, oops, sorry, the that's the h of x part, right? And this part here is the h of y given x. Do you see it?
yes.
Right. So that completes this overlapping circles without any duplication or overlap. So I mean, I'll write it more formally later, but this is the this is another formula for the joint entropy. Right. So just slight modification. We're using the same diagram here, but we have a different formula for computing the joint entropy. So h of x is simple. You could have done it using the oops. Right, so this is simple, which is 0.5 log 2 of 2, right? So this is just equals to 1. Now, the conditional entropy here, we have to kind of average it over the conditional entropies of y given x equals to x. So we have to average over x, h y given x equals to small x. Okay, so let's try to do it. So what is the probability y given x equals to 0, and what is the probability y given x equals to 1? So if x equal to 0, we are here. So our conditional probability is just this arm and this arm. So it's just 0.9 and 0.1. Right, so it's 0.9 and 0.1. So this is 0.9, this is 0.1. This is y equals to 0. This is y equals to 1. This is y equals to 1. This is y equals to 0. So they are symmetric, but it's easy to see from this diagram here, the conditional density. So essentially, what you're looking at is h of x comma y is actually h of x plus h of y given x, right? And from this, basically, h of y given x equal to 0 is going to be it's going to be 0.9 0.1 log 2 of 10. Okay, whatever it comes up to be. So it's the same for both of them. So this guy here is going to be, so this guy equals to 1. This is basically so it's just 2 times so it's basically the probability x equal to 0 times h of y given x equal to 0 plus probability x equals to 1 times h of y given x equals to 1. Okay, and these are both 0.5, so you just compute this quantity, 0.9 log 2 of 1 over 0.9 plus 0.1 log 2 of 1 over 0.1. Okay, so that's the joint entropy. Now, so let's say so let me try to compute this. It's going to be can someone compute this quickly for me?
Point 468.
It's 0.468. Are you doing log 2, right?
Yes.
Let me quickly verify this. Yeah, that's correct. Okay, excellent. So if you look at this overall, it's 1.468, right? The joint entropy. Now let's look at the mutual information. So the I of xy is actually, I mean, you could again use a definition which is h of y minus h of y given x, right? Or you could have done h of x plus h of y minus h of x and y, right? If you look at this Venn diagram here, you could just add the two circles and subtract the joint, so you get this small intersection in the middle. But I think we have these numbers here, so let's look at what is h of y here. H of y is a 1, right? Again. So this equals to 1. And this equals to 1 point.
H of x, it's 1. We need to.
What is it?
H of x was 1. Is it the?
No, h of y is also, because these are the same, you know, these are.
Yeah.
Yeah, because the probabilities are 0.5 for each symbol, both in input and output.
Yeah, but I think we have a mistake because, let's see. No, we are okay. And the joint, the conditional entropy is actually 0.468. Right, so what does that turn out to be? It's
0.5332.
That's 0.532, right?
Okay.
Okay, so now consider the case. So it means there's still some change in entropy of y, or let's say some change in entropy of x when you figure out what y is. So you're actually reducing uncertainty in the input. So now let's consider the case where the bit error probability, or f of the BSC is 0.5. So let's say that the channel is confusing bits at a probability of 0.5. So if you send 0, it's going to be either a 0 or a 1 with a probability of 0.5. That's a huge error, right? So what happens? So now if you do this, basically, you can again do the computation. Eventually, you just have to find out the IXY. And it's again going to be h of y minus h of y given x. So this is already, again, it will be 1 because it's symmetry. And this thing here is going to be the sum over x, right? And then the h of y given x equals to x. So because x is equally likely, the sum goes away, so it's just equals to the h of y given x equals to 0, right? I'm just simplifying it here because it's a symmetric case. Everything will be just twice this term. So computing this is actually because of when f is 0.5. So let's say the f is 0.5. What you will have is simply 0.5 log 2 of 2. Right, so it's going to be 1. So eventually what you see is your information is 1 minus 1 is 0. So this means the X and Y are independent. Meaning what you send at the input and what you receive at the output are completely independent. So they have no relationship. So meaning so you could have sent one message and you would have received another completely different message, which has no correlation, no association with the input. And which makes sense because you are sending an equally likely or equally probable symbol, and that goes through a channel that distorts everything with a probability of half. So that's the most error you can put into the data. And when it gets received at the output, obviously it makes sense that there is no information that you are able to achieve because the reduction in entropy is 0. So you had the same amount of uncertainty in the input that you have at the output. So essentially you are having a 0 information. So the bottom line here, or the message, or let's say the key insight, is that mutual information is a measure of the amount of information transferred. Right? So the more uncertainty you are able to remove from the input, the more information you have gained while going from X to Y. So I think I will write the definitions now more formally. So the I of X and Y is actually, which you saw earlier, it's the H of X minus H of X given Y, and it's also equals to H of Y minus H of Y given X. So whichever is easier to compute, you can use that, but generally this one is easier to compute. And because channel probabilities or channel transition are often known, right? Because you know the probability of Y given X, so you tend to go towards H of Y given X first and then subtract it from H of Y. And if you want to find H of Y, you can easily compute it using the law of total probability. Maybe I can write this here as well. Okay. Now, So again, these are both ways to compute the information or mutual information between two random variables. But the first definition is a little more intuitive in the sense that it tells you, how much uncertainty is reduced. Reduced in X when we look at the output. So in other words, if no uncertainty has been removed, or no uncertainty is reduced in the input, then no information has been transferred. Okay, so for example, when X and Y are independent, the h of X given Y is actually just h of X, right? So the mutual information is actually h of X minus h of X given Y, which is just h of X minus h of X, and it's going to be 0, right? If X is independent of Y. Another way, as I mentioned in today's lecture, the mutual information can also be, it's another so I of X and Y is actually h of X plus h of Y minus h of X comma Y, right? So it depends on the scenario. You can use different methods to compute these quantities. So let's try to do a quick example on, sort of a non-trivial example on mutual information computation, right? And then we will try to find the capacity of the channel, or something called the Shannon capacity. So let's consider, so this is the first example. If you're looking at a binary symmetric channel, with the bit error probability F is 0.15, and probability that X equals to 0 is 0.9. Right, so how would you compute the capacity? I'm telling you that, you had So you had a probability x equal to 0 is 0.9, and you have and obviously probability that x equals to 1 is 0.1. Okay, and your general transition probabilities are 0.15, and then it is 0.85 here. So first thing is, how do we compute the probabilities of y equals to 0 and y equals to 1? Right, so as we've done earlier, I think it should be now very clear to everybody that so we're using the law of total probability. Okay, and I'll just write here, this is the law of total Okay, now probability y equal to 0 given x equal to 0 is 0.85, and probability x equal to 0 is 0.9, and these are 0.15 times 0.1. Right, so what we will get is 0.78, right? And the other one you can compute simply by subtracting from 1, right? So it turns out to be 0.22. Okay, fair enough. Now we want to find out the mutual information, right? So the mutual information between x and y is going to be, again, many definitions, but I think when you're solving problems, the easiest way to get to the mutual information is using h of y minus h of y given x. And the reason is, again, because usually you know the conditional density of y given x instead of the x given y, so this is an easier route. And even sometimes the joint density is not known, so just try to make use of the conditional density. Okay, so let's use this formulation. But remember, this part here is the probability y equals to 0 times probability h of y given x. Oops, sorry, I missed it. This is x equals to 0. H of y given x equals to 0 plus probability x equals to 1 times h of y given x equals to 1. That's the way to get the conditional entropy. The h of y is pretty simple because we already have the probabilities, so it's simply it's 0.78 log 2 1 over 0.78 plus 0.22. Okay, so so let's try to figure out what the joint values are. can maybe just say this is what it's going to be. That's my computation. You can check it. So I'll proceed with finding the conditional entropies. So let's go with the H y given x equal to 0. For that, you need the conditional probability of y given x equal to 0 first. So that's going to be, again, I know immediately that it has to be for y equals to 0 and y equals to 1. And this I can obtain using it could be Bayes rule, it could be by the initial definition. So it's, again, if you consider x equal to 0, basically you're looking at this arm, right? So it's 0.85 and 0.15, right? And the opposite for x equals to 1. So when x equals to 1, you're basically 0.15 and 0.85. So when you have this conditional distribution, then you can find the h y given x equals to 0. And again, it's going to be simply 0.85 log to 1 over 0.85 plus 0.15 log to 1 over 0.15. Okay, and this is actually 0.61 if I'm not mistaken. And h of y given x equals to 1 is similar. So it's 0.15 log 2 plus 0.85 log 2 of 1 over 0.85. And again, from the symmetry, it's again going to be 0.61. So now the what is left is the mutual information. So if you go back to your definition of I, x and y, it's going to be h of x, or sorry, h of y. Or maybe before that, I can just complete the conditional entropy. So it's h of y given x is the average. So it's probability x equal to 0 times h of y given x equal to 0. And probability of x equal to 0 is 0.9 here. So it's 0.9 times 0.61 plus 0.1 times 0.61, which is actually exactly 0.61. Okay, so using this, we go back to your I of xy. This is h of y minus h of y given x. H of y is, as we computed, 0.76 minus 0.61. This turns out to be 0.15 bits. Okay. So that's an example of a capacity calculation for a binary symmetric channel. But I'll do another one for a different type of channel. Then hopefully in the homework, you'll be able to do it for a more elaborate channel called the binary erasure channel, right? So it's the same style, but a little more, you have to be a little more careful computing the probability. So let's go to the second example. Consider a Z channel with F equals to 0.15 and probability X equal to 0 is 0.9. Right, it's the same idea. We start off with, this time the channel looks like a Z, right? So there's only confusion in the symbol 1. So 0 is always transmitted as a 0 with probability 1, and the symbol 1 is confused at F equals to 0.15. So you have this set of probabilities here. And we're told that probability X is 0 is actually 0.9. Okay, so most of the time you send zeros and that's perfectly transmitted on the channel, but sometimes you transmit 1 and that has some small probability of being confused. So this part is actually representing the Z channel. Okay, first step again is finding the probability Y equals to 0 and probability Y equals to 1. Okay, so probability Y equals to 0, again, law of total probability. Given X equal to 0 times probability X equals to 0 plus probability Y equals to 0 given X equals to 1 times probability X equals to 1. So this is 1 and this is 0.9, and probability of Y equal to 0 given X equals to 1 is a 0.15 times 0.1, right? So you will get 0.915 here. And again, probability Y equals to 1 is 1 minus 0.915, which is 0.085. Okay, perfect. So that's the first part where you can go ahead and compute the H of Y, and that's 0.915 log 2 1 over 0.915 plus 0.085 log 2 1 over 0.085, and that turns out to be we compute it right away.
I got 0.4196.
4196. Let me just quickly verify this. I'm hoping you did it correctly. So let's
That's correct.
yeah, is this correct? Okay, perfect. So next part is finding the joint entropy, sorry, the conditional entropy. So H y given x. So we are interested in information between x and y. So it's going to be h of y minus h y given x, right? And again, this part here is writing it again because people still find this a little complicated. So h okay, so finding the h is coming from the probability, right? So we have to figure out what the probability of y given x equal to 0 is. So if you look at 0, you are only here. Right, so y is 0 and y is 1. Your probabilities are 1 and 0. So if x is 0, you are surely 0 at the output. So this will give you an h y given x equal to 0 to be equals to 0, right? And obviously go to the logarithms and figure out the conditional entropy. Now the probability y given x equals to 1 is the other branch, so it's this part and this part. So it's 0.15, 0.85, and our y equals to 1, 0, and y equals to 1. So our h of y given x equals to 1 is going to be 0.15 log 2, 1 over 0.15 plus 0.85 log 2, 1 over 0.85. So it turns out to be, just to verify this. Oh, did we do it earlier? No.
Yeah, slightly different this time. I got 0.6098.
Okay, so perfect. All right, so what is the h y given x? So it's going to be 0.9 times 0 plus 0.1 times right, so it's 0.06 098. Okay, so let's see. So therefore, your information, mutual information, is hy minus hy given x. So it's 0.4196. Can you subtract this for me? 0.06098.
Yeah, 0.3586.
Yeah, 0.359 bits. Okay, so that's the second channel. And important thing to note here, so this information numbers show something. So this is for C channel with F 0.15. So it's 0.359, and this thing here is so it's a BSC. So notice that the mutual information of a BSC is much smaller than the mutual information of the Z channel. So we conclude that the Z channel with the same bit error probability has a higher mutual information, so it's more reliable. So it transfers more information. And it makes sense because you have less confusion here, right? So it's only one of the symbols mess up the inputs, or one symbol is being messed up, the other is just perfectly transmitted. So you have a higher rate of this channel. So Z channel with the same bit flip probability has higher mutual information. Therefore, Z channel is more reliable. Or has higher rate compared to a BSC. Right? Now, we computed the the mutual information for a fixed bit flip probability. But now when we want to find out the capacity of the channel, we look for what is the maximum mutual information that can be achieved by the channel for any bit flip probability. Right, so that will give you the best that the channel can do in terms of mutual information. So the question is, so what is the best a channel can do in terms of mutual information? Right, so remember, mutual information is a function of just the bit error or the bit flip probabilities. Right, you can't change the input probabilities to the channel because that depends on what type of data is being fed. But what you can manipulate or what is different for different channels is the bit flip probability. So essentially that's the characteristic, or that's the defining quantity for any channel. So the question fundamentally is, what is the best mutual information that a channel can achieve with any bit flip probability? So that's called the capacity. So the capacity of a channel is defined to be the maximum possible mutual information. So we say that the C is actually the max of I, X, and Y over the input probabilities. Okay. So I'm sorry, I take my words back. Basically, the bit error probability is fixed for a channel, and what you can change is the input probabilities. So what you want to maximize over is the input probability distribution. You can't change the bit flip probability F that we've been mentioning for different channels.
So we fix F and then we do this calculation
Yes.
for every range of probability of X equals 0 from 0 to 1. Okay.
Yes, so you try to maximize over, if it's a binary channel, you can maximize over a probability of X equal to 0 or X equal to 1. It's the same thing. So you want to maximize this capacity or mutual information over the input probability distribution of the data X. So let's say the distribution Px is called the optimal input distribution. So if your data has that distribution, then you will achieve the capacity of the channel. Okay, so in other words, the capacity C measures the maximum amount of error-free information that can be transmitted over the channel per unit time. So we're basically talking about the rate that can be achieved for communication over that channel. So let's do a simple example on how to compute the capacity of a channel, and it's similar to what we've done, because we eventually are going to find the mutual information, and then the next part is how do we maximize it. That's where depending on how complicated the channel is, the methodology becomes more and more complex. So we'll start off with a very basic example of capacity calculation. Okay, so consider a binary symmetric channel. Now we are going to use a very generic one with bit flip probability F and the general input probabilities probability of X equal to 0 is P, and probability of X equals to 1 is 1 minus P. Okay, so you have a channel which is very generic, and we want to figure out, this is a probability but this is F. This is 1 minus F. And the probability X equals to 0 is P. And this is 1 minus p. Okay, and we want to find the maximum capacity or maximum mutual information that this channel can achieve. So we'll proceed with the same method that we've been using in our previous examples, but this time it's generic, so we don't have numerical answers. So again, probability of y equal to 0 is going to be this expression here, given x equals to 1 times probability x equals to 1. So y equal to 0 given x equal to 0 is 1 minus f times p plus f times 1 minus p. So if you expand it, it's going to be p minus pf plus f minus pf. So basically it's p plus f minus 2pf. Okay. And similarly, probability y equals to 1 is going to be 1 minus p minus f plus 2pf. Right, so it's going to be 1 minus, well, I think we can factorize them a little bit more, saying that this is actually p times 1 minus 2f plus f, and this is 1 minus p times 1 minus 2f minus f. Okay, so let's write them here. Okay, so there you go. And next step is using conditional distributions to find h of y given x, which is probability x equals to 0, h y given x equal to 0 plus probability x equals to 1, h of y given x equals to 1. So let's see what h of y given x equals to 0 is. You have to first look at the probability, and it's going to be 1 minus f and f. So this is y is 0, y is 1. So your h y given x equals to 0 turns out to be 1 minus f log 2 1 over 1 minus f plus f log 2 1 over f. Okay, and let's call this thing here. Let's introduce a new notation. Small h2 of f. So if you have, so note h2 of f is actually f log, f log 2 1 over f plus 1 minus f log 2 1 over 1 minus f. If you have just one parameter, and that's like a binary variable which can take two values with the probability f, then its entropy you can just represent with a shorthand of h2 of f. It's just for convenience, because this is a long expression here. We know that it's log base 2 kind of entropy definition with a parameter of f, and there's a complementary term next to it. So let's try to create a shorthand for it. So this thing is just a shorthand notation. to make our life simple, because it's going to be more messy if you keep carrying this forward. But you know this.
I got a question. Is it 2H2 because we're only using two symbols on input and output?
No, this is because you're using log base 2.
Okay, well, I guess the further question for that would be the reason we're using log base 2 would be because we have two symbols, or is that incorrect?
No, that is incorrect.
Okay.
We're using log 2 because we want the result to be in bits.
0 and 1, two symbols.
No.
Sorry.
I mean, you can have as many symbols, but the thing is, this logarithm is going to convert the result into bits.
Right. Yeah.
Binary bits. Like, so log 2 of x will give you result in bits, right? And log e, or natural log of x, gives you the result in nats. So it's the unit difference.
Yeah. Okay.
So log 2 of 2 is just 1 bit.
All right. Perfect. Thank you.
So that doesn't have to do anything with the, F1 minus F. You can have more and more terms, but it's just the units of the result is binary bits. Okay, so I'll keep this here, and our conditional probability is just H2 of F. And similarly, if you look at the other one, which is the probability y given x equals to 1, again, it has the similar structure, but it's inverse. So again, I think because of symmetry, it's going to be H2 of F. Okay. Now, I mean, I can maybe give you a more general definition of H2 notation, because I think it's just confusing some people. So H2 of P vector, where P vector equals P1, P2, Pn, is the shorthand for P1 log 2 1 over P1 plus P2 1 over P2 plus dot 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 plus Pn log 2 1 over Pn. Okay, does that make it clear?
Yeah, that's perfect.
Okay, so if you just have a vector, you compute the P times the log of 1 over P, and then add them up, it's just H2 of P. Okay, the other term is again the same, so what we end up with is the H y given x, so it's going to be, what is the probability of x equal to 0? That's P. It's going to be P times H2 of F plus 1 minus P H2 of F, so it's just eventually going to be H2 of F. Okay, now the mutual information. So the mutual information I, x, and y is h of y minus h of y given x. And we already figured out what h of y is. So h of y is so we have these probabilities, and we have to kind of do an h2 of this. So I would just write it as h2 of p times 1 minus 2f plus f. Okay. And then the conditional one is just h2 of f. Okay, now that's our channel capacity. And sorry, that's the mutual information. Excuse me. So the capacity is actually the maximum mutual information. So we can say that the capacity is the maximum mutual information. Right, so that means the C is the max of I of x and y over the P, right? So P is the input distribution. P is the parameter. So once you know P, then the 1 minus P is obvious because you just subtract it from 1. So essentially, you just need to find out just one parameter P to figure out the input distribution that maximizes your mutual information. So let's try to replace this I with the quantity here, so that C is actually going to be the max over P of this thing, H2 of P1 minus 2F plus F, and then minus H2 of F. Okay, so notice that your P actually only appears in the first term. So P only appears here. So there is no P in this term. So that simplifies our job a little bit, because if you just maximize the first term, that's it. That's your maximum. That is a P that will maximize it. So essentially, we can just drop the second term, and you find the channel capacity. So the question is, what is the P that maximizes your I, X, and Y? Okay, so in other words, so how do we maximize H2 of P times 1 minus 2F plus F minus H2 of F with respect to P? Or for some value of P. Okay, so I mean, it's not a big deal. We can just borrow the classical concepts from calculus and say, why don't we find the sensitivity of this quantity with respect to P? That means we take the derivative, right? We see how sensitive this quantity is with respect to P and find out the stationary point. So solve, d over dp, h2 of P, 1 minus 2f, okay, and then put it equal to 0, which in other words is just taking the derivative of the first term because second term does not have a P there. So okay, and that will give you the P. But interestingly, the entropy function is a concave function. So the P that you find is going to maximize this quantity, because otherwise you will have to do a second derivative test and find out the curvature of this quantity and say or argue that this indeed is the maximum value. But in this case, unfortunately, you're in a situation where the function itself is concave in the argument. So remember, this thing here is, so h2 of anything, right? So h2 of a number, h2 of alpha is just alpha log 2 1 over alpha plus 1 minus alpha log 2 1 over 1 minus alpha, right? And h2 of alpha is concave in alpha. The reason it's concave is because it looks like this, right? And it's maximum at half. We've seen this function before. So it's concave in alpha, and so the result equating the derivative to 0 is a maximum, or it's a global maximum, right? Okay, very good. So our job is simply to differentiate this and then figure out what the maximum P is, or what's the P that maximizes this. So let's try to do it. So we'll have d over dp of this h2 of this. So basically we have p1 minus 2f plus f log 2 1 over e1 minus 2f plus f plus 1 minus p 1 minus 2f minus f times log 2 of 1 over this 1 minus p 1 minus 2f minus f. Okay, so we have to take the derivative of all of this and put it equals to 0. Okay, so if look at the first term, basically you have a product of two functions. So you keep the first one and then take the derivative of the second one. So we'll keep p1 minus 2f plus f as it is. The derivative of log 2 of this is basically 1 over this, so that's p. That's going to be P1 minus 2F plus F. Okay, and then we'll have the derivative with respect to P, which will be 1 minus 2F here. Okay, and then you have a plus and then a log 2 of 1 over P 1 minus 2F plus F times the derivative of the first term with respect to F, oh sorry, with respect to P, which is 1 minus 2F. Actually, a better way of maybe more easier one is to just get rid of the fraction and replace it with a negative sign. So instead of writing this whole term with the fractions, just let's try to write it as, I'll put a negative sign here. So instead of log 2, 1 over this, so let's say this thing here is equals to minus log 2. Right, so it's just putting a negative sign here and getting rid of the fraction. So what we will get is negative P1 minus 2F plus F log 2 of P1 minus 2F plus F. And then we'll have the same negative 1 minus P 1 minus 2F minus F times log 2 1 minus P 1 minus 2F minus F. Equals 0. So we get here is first term, which is minus P1 minus 2F plus F, right, times 1 over P 1 minus 2F plus F times 1 minus 2F. So luckily these two will cancel from the first term. And then the second term is with the log, so you have log of P 1 minus 2F plus F as it is. Then you multiply with the derivative, which is basically it's a negative here because it's a 1 minus 2F outside. Okay, and the same thing with the second term. So you have a negative 1 minus P 1 minus 2F plus minus F on the top, and you have the same thing here at the bottom times negative 1 minus 2F here. The second term has a log, so you have 1 minus P 1 minus 2F plus F, and then there's a 1 minus 2F outside. So you have to equate this to 0. Again, this fraction cancels out and you are left with negative 1 minus 2F here minus 1 minus 2F log 2 P 1 minus 2F plus F plus 1 minus 2F plus 1 minus 2F times log 2 1 minus P 1 minus 2F minus F. So this thing here cancels and you just have log function. So you can combine the two log terms and will be 1 minus P 1 minus 2f minus f at the top, and then at the bottom you have p 1 minus 2f plus f, and this is equal to 0. Since we have the log, so basically this fraction whole should be equals to 1. So in other words, 1 minus p 1 minus 2f minus f over p times 1 minus 2f plus f equals to 1. Oops. So if you cross multiply, it should be equals to p 1 minus 2f plus f. Okay, so you get p times 1 minus 2f plus f equals to 1/2. So eventually p is going to be 1/2 minus f over 1 minus 2f, okay? Which is going to be equals to 1 minus 2f over 2 divided by 1 minus 2f. So it's just 1/2. So therefore, your p star is equals to 1/2. So that's the input distribution that maximizes your capacity. So therefore, inputs or equiprobable maximize the mutual information of a binary symmetric channel. So just anecdote here, you know, a more elegant way to solve it would have been way to solve would have been that you maximize over P the H2 of P1 minus 2F plus F. So if you're a bit smart, you can note that H2 of alpha has a maximum value 1 for alpha equals to 1/2. Right, so that means that, so since H2, or since maximum of H2 P times 1 minus 2F plus F equals to 1 for argument 1/2. So P times 1 minus 2F plus F equals to 1/2. Okay, for maximum or for maximization. Okay, so therefore P is 1/2 minus F over 1 minus 2F, and it's going to be 1/2. Okay, so you see that with just a little you know, smartness, you can actually avoid all those computations and come up to the final result. But obviously this may not be obvious and may not be possible in all cases. So a traditional way to do it is try to find the derivative and equate it to 0. And you can also test it for the second derivative, but generally in entropy functions, it's a concave function of the input argument, so you may not need to go there. And eventually you will find the maximizer or the distribution that maximizes the mutual information. And the capacity itself is the maximum value. So you have to be a little more careful here. So the capacity of a BSC is therefore C, which is the maximum of the input distribution of I, X, and Y, and it's H2 P star 1 minus 2F plus F minus H2 of F, right? So remember we had two terms. We maximize the P star, we maximize this for the P star and the P star equals to half. So we can just plug it back in and find the capacity. So it's simply H2 half 1 minus 2F plus F minus H2 of F. It's going to be H2 half minus F plus F, right? So it cancels away. And it's going to be H2 of half minus H2 of F. And essentially it is 1 minus H2 of F. Right, so therefore this C of a binary symmetric channel is 1 minus H2 of F. Right, or in other words, it's 1 minus F log 2 1 over F minus 1 minus F log 2 1 over 1 minus F. And if you go back to our first lecture in this course, we saw this expression there, and we said we are going to reach there in a few lectures, and there we are at the capacity computation of a binary symmetric channel. Maybe that expression was written in a different form by replacing these with negative logs. So we can do that also here. Let's say this is 1 plus F log 2F plus 1 minus F log 2 of 1 minus F. Okay, so that's the important thing to note here. Okay, so we are almost.
How did you change the sign to positive?
Yeah, I'm saying that so log A of 1 over X is actually equals to log of
Okay.
1 minus log A of X, right? So this is 0 minus.
Good, thank you.
This is just a note here.
And for the shortcut, are we assuming every time we use a log function, we have this concave function that we can?
No, I mean, it's by realizing the fact that if you want to maximize this, you know,
Only
this
when
thing
you
here.
ask for maximum, for this maximum.
Yeah, if this has to be the maximum, then the whatever is inside is should be equals to half.
Right.
Because this H2 function is maybe I'll just draw it here. So if this is alpha, this is H2 of alpha. You know, we've seen this before, so it's like this. Right, so it's maximum entropy here. But I mean, you don't have to act smart. It's up to you. If you realize this, that's great. Otherwise, you can do the derivative and eventually get to the final maximizing distribution. And when you plug that value into the C, you will get the maximum capacity. It's important to understand that just writing the P star is not the capacity. The capacity is when you plug this P star into the expression. So this is your expression. So if you put this into here, that's the capacity. You have to also take into consideration the second term, which we just got rid of earlier.
Okay, thank you.
Okay, so I'm going to write a quick few summary points and some broad overview of the Shannon noisy channel coding theorem. That's going to give you a broad view of what is happening and what did we find, and what is really the noisy channel coding theorem and why it's so important in information theory. So the noisy channel coding theorem says that for every discrete memoryless channel, the channel capacity C is equals to the max of I, X, and Y. And this maximization is over the input probability distribution, right? So excuse me for saying that it's the maximizer over the bit error probability. You can't change the bit error probability because that's characteristic of a channel. So this is the input probability distribution. Okay, so the channel capacity C actually has the following property. So the property says that for any epsilon which is positive and rate R which is less than capacity, for large enough n, I think we've mentioned this before, but I'm just reiterating for your understanding, there exists a coding and decoding algorithm. There exists coding and decoding algorithms such that the maximum probability of block error is less than that epsilon, right? So for any small epsilon, you can actually reduce the maximum probability of block error to something lower than epsilon if you have large enough n, which is the block length, and you will achieve a rate R which is less than C. We will see what that means. So yeah, I'll go ahead and draw that old diagram for you again. So we had the rate R, and we had the bit error probability PD, and we said, there is somewhere a capacity sitting there for which you have arbitrarily low probability of error, and there is a line that goes here. So what the first part says is, that for any discrete memberless channel, there's a capacity C sitting there, and that's something where you are able to live here, so you can. Right, so let's mark it as so it's not only this, but essentially you're able to be in this regime. So there's right, so for R, which is less than C, so you can be within the capacity, and you can achieve arbitrarily error probabilities based on what block length you choose. So essentially, it is possible to have a coding and decoding strategy that allows you to live here. That means you have a strategy which achieves a capacity which is somewhere here, and a bit error probability which is somewhere in this region. Now the second part of the noisy channel coding theorem says if probability so maybe I'll just turn everything the same color, so you have okay. Second bullet says that if probability of bit error PB is acceptable, rates up to function R of PB are achievable. Where R of PB equals the capacity C over 1 minus H2 of PB. Okay, and basically that's the line here. So maybe let me try to change the style here. So that's the line. That's the so this line is R of PB, right? A function of the bit error probability. This is actually C over 1 minus H2 of PB. So if PB is 0, then H2 of 0 is 0, so you're just at a C. But if you have large probability of bit error, then you obviously go above the capacity. So this is a straight line here. What the second part of the theorem says is that if you're willing to accept errors, right? So if you say, okay, errors are fine, then you will be able to go up to rates that are in this region. So you can go up to this line here. Okay, so this region where R is in this part and PB is in that part, you can achieve that, but you will have to accept a certain probability of bit error. Okay, you cannot have zero, right? So in all of this region, there is no zero bit error probability. It's always some positive bit error probability, right? Pick any point here, here. Okay, and I'll say this is really so this is communication with errors. And there is a whole theory that discusses this region and tells you how to encode and decode using schemes that will allow you to be within a certain error limit. And that theory is called rate distortion theory, and it's not going to be part of the course, but at least you should be familiar with what we are talking about when we say rate distortion theory. So that's their subject. They deal with this region. And the third part of the theorem is telling you that anything beyond this is not achievable, right? So for any, so you have defined regions where you can have a certain bit error probability and you can achieve a certain rate, but regardless of the rate, for any bit error probability, you cannot achieve a rate which is greater than this line here. So rates greater than RPB are not achievable. So that's the beauty of the theory. It tells you, no matter how good you are, you cannot live here. This is beyond your reach, so you cannot go here. Right, no matter how high bit error probability you're able to tolerate, you cannot achieve anything which is higher than this rate function, R of PB. And I think that was the fundamental contribution of Claude Shannon, and that brought him this fame for information theory. And I think this theory was extended in many, many different dimensions, analyzing many different channels, and a lot of work has been done in this domain, following these fundamental ideas. So what we're talking about in this course is really the basics, and you can delve deeper into any of these domains if you have interest, and you are required to work on projects, then I think this is the basis. So before we end our discussion, I will just write a summary of how to computing channel capacity. So the goal is, or the process, I will say, is to find the optimal input distribution using derivatives. Okay. And then go just use the optimal input distribution to compute I of xy right, or C. Let's say C is the max of E star, or let's say the X star of I xy. Okay, the flow is the following. So you have you first find, let's say this is step 1, you find the I of x comma y, right? So you can use different methods, but I suggest for channels, generally, people like to use h of y minus h of y given x. Okay. And again, you may have to go through multiple processes or steps to reach h of x or h of y given x, but hopefully you are able to reach there, and then you can move forward with the second step, which says, find the partial derivative with respect to the PIs. Okay, PI meaning the probability of x equals to I, to find the sensitivities. Of mutual information to input distribution. And then pretty straightforward, where you equate curly PI equals to 0 for all I. Okay. And then the next step is to obtain PI star, right, which is the optimal input distribution. And then final step is to substitute PI star in IXY to obtain C. Right, or the maximum mutual information. Okay, so with that, I would end our discussion today, and just mention a few announcements for you. We will be having our homework due this week. So you will have opportunities to compute mutual information of different channels and find their capacities and things of that sort. So please go through these examples, see how these are done, and then homework will be an opportunity for you to test out your skills. Will be due next week. Okay. So you find mutual information. Okay, and then I think project abstracts, I have received them, and then I'll go through them quickly, and I'll give you feedback hopefully next week, to see if there's some changes that need to be done. So projects will be reviewed and feedback shortly, right? So keep looking out for messages on Canvas. Okay. So, or messages or comments, right? So under your assignments, you will have a comment saying if it is okay or if something needs to be changed. So, but nevertheless, I would say you start working on your projects in the meantime. Start reading out papers and collect as much information as you can that is required for your specific idea. And if you need individual support, then you can get in touch offline and we can talk about it. And yeah, that's it from my side. If you have questions, just let me know.
In this flow that you just described, in this PI is the P that we just derived earlier, right, Professor?
Yeah, this is general case. In our case, we have a binary input, so we just have one parameter, P, and the other one is 1 minus P.
Okay.
But let's say you have 4 inputs, then you will have P1, P2, P3, P4.
Okay.
So it's a general kind of description of the process. And you're right, in our case, it is just the P.
Okay. Thanks.
Okay, any other questions? Or feedback? I mean, if things are too easy, too hard, too anything that you want to talk about.
No, I think we're going at a good pace right now.
Okay.
At least I'm able to follow material pretty well, so I appreciate that.
That's wonderful. But anyway, if you have any questions, comments, feel free to send me an email, and then we can set up a session to discuss them. And hopefully I'll see you next week then.
All
Okay.
right, thank you.
All right. Have a great rest of your week.
Yeah,
Bye-bye.
easy.
Thank you, you too. Bye.